This presentation provides a brief introduction to integrated protection planning-based simulations, commonly known as IPPS environments. What has given rise to this interest in improving the modeling of protection relays and special protection schemes within standard planning dynamic studies? There appear to be two main contributing factors. Firstly, classical short-circuit calculation assumes the system is always in steady state after disturbances. In doing so, it ignores dynamics governed by generators, loads, and control devices. Furthermore, it does not consider voltage, frequency, and power transfer related elements such as out-of-step and power swing blocking, nor does it consider the time-varying quantities such as fault current decay. A simple example can be seen here, where a remote fault gives rise to a Zone 1 distance operation some 2 levels away as a result of a post-fault power swing on the system. It can be seen that several legitimate protection operations isolate the various contributions to the fault, but the post-fault power swing on the system enters the Zone 1 of a remote protection device, resulting in an unexpected operation. The second factor contributing to the interest in IPPS environments is that transient stability programs currently either rely on theoretical protection relay operating times or employ simplified protection models using generic relay representations that simply mimic the main protection elements and assume that the supervisory elements operate. Furthermore, these simplified models require a conversion of the actual relay taps to derive the equivalent settings for the generic models. An obvious problem with using the operating times derived from steady-state assessments is that the prospective fault levels often used in these assessments may not persist. Synchronous generator contributions decay as fluxes re-establish their paths, and the machine reactance transitions from the subtransient to the transient and back to the synchronous values. In this example, the steady-state analysis assumes the prospective fault level persists, and it predicts a relay operation. The IPPS analysis, by contrast, investigates the protection response using the actual fault current that presents on the system, and it determines that the relay element is stable, as the fault current does not remain above the setting threshold for the entire delay time. A lower setting or a shorter time delay is required if the system security relies on this protection operation. Another problem with assuming steady-state predictions of protection operations is that the static relay characteristics, shown in blue here, can be inaccurate under fault conditions. This can be seen if we construct the system view by computing the apparent location of relay operations in the positive sequence plane, calculated using the actual network currents and voltages in the detailed relay comparator equations. It is seen in this example that the dynamic characteristics are modified from the self-polarized Mohs circle. Operation is up to the set point for line-to-line faults, but it is in a more limited region for single-line faults. The region below the origin indicates operation for forward faults with capacitive impedance. Simply applying the steady-state expectations of the relay operation in the dynamic simulation can lead to an incorrect relay operation and misleading predictions of system recovery. Recognizing these factors in the aftermath of the Northeast blackout, the Federal Energy Regulatory Commission, FERC, mandated the Western Electricity Coordinating Council, WECC, improve the modeling of protection relays and special protection schemes within standard planning dynamic studies. It is understood that this mandate was the catalyst for the development of IPPS environments that we are looking at in this presentation. The development of IPPS environments was not without its challenges. For unbalanced faults, which are typically represented as balanced faults in the positive sequence network of transient stability calculations, it was necessary to recreate an unbalanced set of three-phase voltages in the protection simulation from these positive sequence voltage profiles obtained at each time step of the transient stability analysis in order to determine the actual relay response. There also needs to be alignment between the network models in the system dynamics and protection simulators. The alignment of these models can be complicated by the use of detailed bus structures in the protection simulator, for example, breaker and a half and ring buses. A sophisticated protection system model is also required, and not simply an abstraction of the main protection elements into generic relay models. The representation of the protection system contains relay-specific models that capture the actual comparator equations, supervision elements and internal logic, and tap settings that have been implemented by the relay manufacturer in their devices. Furthermore, it must also capture the configuration of the utilities protection scheme logics, for example, POTT schemes. The following example shows the power swing elements, together with the associated internal logic and relay tap settings, of a common relay. So what then are the potential applications for IPPS environments? With the frequency and the nature of changes occurring in today's power systems, periodic reviews are required to ensure secure operation is maintained as electrical centers move and power swing speeds increase with reduced synchronous machines online. With IPPS environments, instances where selective fault isolation exceeds critical clearing times can easily be identified. More importantly, the IPPS analysis can identify unexpected miscoordinations due to system dynamic behavior. In this example, the system response to a Zone 2 clearance of a fault gave rise to a power swing detected by upstream relays not equipped with power swing blocking. It is important to remember that the IPPS analysis is not considering the response of a single relay. Rather, it examines the performance of the system protection as a whole and identifies any protection operations on the system, which it then incorporates in the dynamic simulation to determine if the system recovers. IPPS environments can also be used for postmortem event investigations and analysis. This example is a paraphrase of an event described in the following reference. A lightning strike caused the loss of 800 megawatts of regional generation. The subsequent 800 megawatt import from neighboring networks was seen as a power swing at frost and trouble. But the slow speed of the swing resulted in power swing blocking action, and the protection remained stable. On other parts of the system, the protection was not equipped with power swing blocking and was tripped by the power swing intrusion into the distant Zone 1 characteristics. The loss of generation support from the neighboring network resulted in an under-frequency load shedding of some 600 megawatts, which was represented in the IPPS simulation. With the loss of local load, the second slip at frost was much faster, and the power swing resulted in an outer step trip of the HV intertie, which completely islanded the network. A further application of IPPS environments is for the prototyping of remedial action schemes. This example considers load shedding operations in conjunction with actions initiated by power swing quantities to develop a remedial action scheme for the islanding of a network. The performance of the staged load shedding operations and actions initiated by power swing quantities, in this example the positive sequence voltage at a substation falling below 0.8 per unit, can be tested and further developed in the IPPS environment. EMT applications provide instantaneous values of voltage and current, which are supplied to the detailed protection system models. Further developments in this area would therefore provide a viable tool to study the behavior of protection on the first cycles after an event triggering transients in the power system. This has been a very brief introduction to IPPS environments, and it may have raised a number of questions. I would be only too happy to address these for you if you would like to send them to me on the email address shown. I would also like to thank you for taking the time to view this presentation.